Alright, so in this final video for the course, I want to talk about processes. And this is an operating system notion, right? We've been working with C and Bash, and those are programming environments or, a shell program. But processes are more about, what's kind of happening outside of one individual program. So, in reality, when we are sitting in an operating system like Linux, there's a number of things running simultaneously. Right now, there's over 300 different things running or waiting to run on my system. So Simple Screen Recorder is the program that's recording this video right now. Pulse Audio is taking care of the audio system. This is a window manager for displaying things. And there's hundreds of these things sitting on the system. Some of these processes are created when the system first boots, which was, on this machine a few days ago. Some of these processes are created by users when they want to execute commands. So to keep track of all of this, there's a unique ID called a process ID, PID, associated with each process. Process ID 1 is one of the first processes created on the system, and these low numbered process IDs were all created at boot time. My Simple Screen Recorder is process 64700, so that's a process that was created just a little while ago. It's been running for about 100 seconds of CPU time, and it's consuming a good chunk of the CPU because it's a fairly intensive process. So the top command, which is what I'm running here, shows me kind of a high-level view of everything happening on the system, ranked by most CPU intensive processes on down. But typically we're more interested in, the processes that we've created and so on and so forth. So PS is the easiest command for looking at processes. Now if I just say PS, I see two lines of output. I see one which says, the command is bash, and here's the process ID. And then I see another command, PS, with a different process ID. Well, if I say PS again, I see bash again, and I see PS. The process ID on bash is still 64720, but the process ID on PS is different. It was 64939, now it's 64940. So this PS is a different process from that one. So in fact, when I type a command, the command executes as its own process, and when the command is finished, that process goes away. And if I say PS again, a new process is created, in this case ID 64943, it executes and it leaves. But my bash process is still 64720. That's the process that started running when I logged in to this console window. So if I say PS-L, I can get more information. I can see the command, how much CPU time it's taken, where it's running. So this is, used to be a physical teletypewriter, TTY, now it's a pseudo terminal, PTS. The priority that it's got for scheduling, the state, so my bash process was sleeping while PS was running, and PS was in the run state. That's what the R means. User ID 1000, that's my user ID, so that's me. But there's a new column, parent process ID. So the PS command in this case, was 64944, but its parent's ID was 64720. Well, that's bash. So this is telling us the PS command was created by the bash process. And bash's parent process ID is 64714. So if I were to do PS-ELF and search, which will show me all the processes, and search for 64714, I see 64714 is this thing called user bin console. And that's the process that created bash. Alright, and I have another bash process running that's sitting over here in this window. And that's got its own process ID, but its parent is also 64714. So console created both of these bash sessions, and in this case, one of those bash sessions created the grep command and the PS command, which had finished by the time this output was being displayed. Alright, so what's process 7170? Well, let's do PS-ELF and search for 7170. And 7170, its parent is process 1. Right? And that's sort of the starting process that creates most of the other processes on the system. And that was created when I did a Control-Alt-T, which started a new console window. If I do Control-Alt-T again and I say ps-l, right, I see a different bash session. Its parent ID is 64961. And if I look at 64961, that's a console process, and its parent is 7170, which is, again, this XF settings daemon. That's what the D at the end means. That's the process that creates other processes. All right, so every process has a unique ID, and if we say ps-elf, we'll see every process on the system. So, you know, there's a few hundred of these, and it starts with process 1, and it builds up from there. So parent process of 1 is 0. That's the actual original process. And these are all processes that were created at boot time. But then some of these higher numbered processes are created kind of on demand. So these are still boot time processes. And these are processes that I ran yesterday to start Minecraft servers on different machines. And then, you know, these are owned by that initial process, process ID 1. Here's my mail client, good old Thunderbird, and so on. So everything that's happening on your system is a process, and it has a unique process ID associated with it. So if I want to see processes just associated with myself, I could say user Nick. Well, there's going to be a lot of them because, you know, I'm the one who logged in to this session. But a lot of these are not associated with a physical terminal or a pseudo terminal, but some of them are. So over here is process 64859. That's a process called sleep. Well, that's something that I'm running over in this window over here, along with VI, 64860. So if I do a PS, I can see I've got a VI process, 64860. I've got a sleep process, 64859, and my usual bash and PS. All right, so that's a high-level view of processes. What can we do with them? Well, when we run a command, here's my PS command. Let's say that I run a command like VI file, and I'm typing, and I'm here in command mode. If I hit a Control-Z, that will stop my command, but the command doesn't actually die. If I do a PS, I still have VI sitting out here. Now I can go back to running that command by doing FG, which says foreground, and I'm back to where the command is. Or I can Control-Z and I can say background, and that will say let it run in the background, even though I still have control of the console here. But that will stop running when it needs input or output from a user. But if I were to say sleep, and let's say sleep 2000 seconds, right? So this command is sleeping, and, you know, if I try to type, it's ignoring me because, you know, the sleep command is running. But if I hit Control-Z, it stops the sleep process. So now if I do PS, I've got sleep, I've got VI, I've got my usual bash and my PS command. And if I do PS again, right, same process ID for sleep, it's the same process. But it's not actually running, it's paused right now. Now if I want to run it in the background, I can say BG, and now it's continuing to run in the background. If I want to bring it into the foreground, I can say FG. Let me get rid of that. I can say FG, and now I'm running the sleep command in the foreground. And again, you know, it's ignoring what I type. So let's do a ps-l. There's the sleep command. Its state is T. If I say put it in the background and I say ps-l, sleep is now in a sleep state. So we can monkey with the state of these commands We can have them running in the foreground. We can stop them and leave them paused. We can leave them in the background but continuing to run, or we can bring them in the foreground, and if we're in the foreground we can hit Control C to stop them. So being able to swap between processes and interact with processes can be useful. For example, you're editing a file in VI and you're going to be using string functions and you can't remember what the name of the include library is, right? You can hit Control Z, say man string length, and then right there it says, oh yeah, include string.h. So you can FG back into VI and then put in that include, and then you go on and you write some code. Now you can't remember what the fgets command was, so Control Z and do a man fgets and figure out what you need, and then FG to go back into VI and so on. So it's a useful way to sort of suspend a command and then get back to a prompt and be able to do other commands while your first command is still sitting around waiting for you. So let's play with this a little further. Let me just put some jobs out here. Let me have a job that's sleeping for 1,000 seconds, another one that's sleeping for 2,000, and another one that's sleeping for 3,000. And so I've got 3 jobs sleeping. Now you notice each time I stop my job there's a number next to it in brackets, bracket 3, bracket 2, bracket 1. So if I say jobs, that will show me a list of all my jobs that are sitting out there right now. So if I say foreground %1, right now I'm running my sleep 1000 command, and if I hit Control Z, that stops it. And if I say jobs, I can see that that job is stopped, whereas these commands, sleep 2000, sleep 3000, these are still running. I can bring my sleep 3000 into the foreground and then stop that. And if I look at jobs, now I've got my 2000 sleep running, my other jobs are stopped. If I want to let job 1 continue in the background, I can say background %1. And now when I say jobs, job 1 is in the running state. And if I wanted to run job 3 in the background, I could say background %3. And now job 3 is running in the background. And if I want to bring job 2 into the foreground, I can say foreground %2. And now it's as if I had just started executing this command. And if I hit Control C, that will interrupt it. And so now I just have my jobs 1 and 3 sitting back there running in the background. So the sleep command is just an example, but you could have a job that you're running that's doing some calculation that's going to take 10 minutes, and you don't want to sit around doing nothing for 10 minutes while this job is running. And so you can run it in the background like this. I can terminate a job by bringing it to the foreground and hitting Control C, but I can also use a kill command. So I can say kill %1, and it'll say terminated, and it's not out there running anymore. And I can say kill %3, and that'll terminate it, and now all 3 of those jobs have gone away. You can also run a command and immediately put it in the background by putting an ampersand after it. So space ampersand means go ahead and run it in the background. So it's running, and now it's just as if I had run the command normally and hit Control Z and typed BG. I can say foreground to bring it to the foreground. I can stop it with Control Z. I can background it. And if there's only one job, I don't need to say %1. I can just say FG and it'll bring it in the foreground, and Control C will stop it. And now all those jobs are gone. All right, so that's a little bit about how we can interact with processes from the command line when we're trying to do multiple things and we want to get back to a command prompt while we have other things running in the background. We can also interact with processes from bash scripts. And so let me write a simple bash script. I'm just going to call it A. All right, so here's a script which is just going to say hello every second. And I'll make it executable and run it, and so, you know, it's just kind of hanging out, saying hello. Now if I control Z it, it stops, right? And it's still, you know, listed as a job, but it's in a stopped state, so it's not running and saying hello. If I say background, now it continues to run in the background. But I still have, you know, control of my terminal window. It's just that there's this job sitting in the background running that every second is displaying hello to my display, my standard out. But that job is still running, but I'm actually sitting at a command prompt. So if I say kill %1, right, it stops outputting, and when I hit enter again, it says that job was terminated. All right, well, there's an interesting command we can use, which is trap. Trap is something we can put into our bash script, and the syntax is trap followed by a command. So I'll just echo haha, and then followed by the name of what we call a signal. And a signal is something like hitting Control C or hitting Control Z, and we can see a list of signals by saying trap-L. And these are the different signals that can be sent to a process. Signals are ways of letting a process know something. So sigint is a way we can interrupt a process. Sig quit is how we can tell a process to quit, and so on. So let me do this. Let's say trap echo haha sigint. So the idea is, if this process gets this interrupt signal, instead of doing what the interrupt signal normally does, which is terminate the process, it's just going to say haha. So let's go ahead and run this, and it's sitting there, and every second it's saying hello. And when I hit a Control C, instead of terminating the process, it says haha. And you know, if I hit a bunch of Control C's, it's doing that echo statement instead of you know, terminating the process. So now we have a process that's a little harder to kill. You can hit Control C, and it doesn't go away immediately. And you know, this is something that, like, you know, VI does, for example. When you hit Control C in VI, it says type :QA and press enter to exit Vim. So this is a useful capability. So what do we do about this? Well, there's a number of ways we can deal with this. We could just do a Control Z and then kill it. But let me do something a little more interesting. Let's do a PS user nick, and it looks like there's this process A sitting right here, 66944. So let's do a PS-long on user nick. Right, so here's the process that's running. It's process 66944. So I can say kill 66944, and the kill command is a way to send a signal to a process. So normally we say kill %1, it means send a signal to, you know, whatever job I have in the background. But I can also specify a process ID, and this will send a kill signal to this process that's running the command A. And when I do that, the script is terminated, right? So kill is not a interrupt, it's a terminate. So let me run this again. It's saying hello, and let's do the PS again. So our process ID is 67116, and let's kill with a sigint that process. And the script gets that interrupt signal, and it says ha ha ha. And it doesn't interrupt it, right? It goes ahead and it says ha ha ha, and then it continues. All right, so suppose I come in here and I say, let's also trap sig term. So now my job is running. And as usual, if I hit Control C, it doesn't stop. I can hit Control Z to stop it, and if I say kill %1, it says that it's terminated, but instead of actually terminating, it just says haha, and it continues running. And if I Control Z it again, well, it's already in the background. So if I kill %1, it says terminated, but it prints out the command I'm running in response to the trap, and it continues looping. So how can you kill this? So if you kill -9, 9 is untrappable. So killing with a signal 9, %1, that will terminate it. And that one cannot be trapped, right? There's no way to intercept a kill with a signal number of 9. So trap 9, that's a sig kill, untrappable. But we can also use this to respond to other things. Like, for example, we could set up something to trap sig user 1, and then we could kill with a signal of sig user 1, and use that as a way to send a message basically to a process. So this is one way we can start having processes interact with one another. And typically we would use a signal to say something like, hey, there's a message for you, go read it, right? I've got some instructions for you sitting somewhere in the system, go ahead and take a look and see what I've said. And there's lots of different signals, right? When you try to divide by 0, you get a floating point exception. The way that's handled is a sig floating point exception signal is sent to the process. And you might trap that, or you might just respond to it by saying, floating point exception, and your process terminates. So this is a general mechanism that can be used to send messages between processes. All right, so we have a little bit of control over processes executing under bash. The more interesting situation is when we start trying to work with processes from C. So let me tell you up front, this is something that you'll get into a lot further in other courses at a university typically, when you do things like system programming courses. But I want to give you a bit of an overview of it here, and we'll also talk about multiple processes and some of the details of dealing with multiple processes in CSE 223 and Spring when we talk about threading in Java. But just to give you an idea how some of this works in C, so let me make a C program. All right, so I'm going to make use of a sleep command, and sleep is a callable function that comes from Unix standard. So let me go ahead and include that. And if I just do this, right, just have something call sleep 20. Right, I can run that, and it'll just hang out in the background for 20 seconds. And if I do a PS, right, there's my test command hanging out and running. And after 20 seconds, it will just kind of silently go away. So it's probably pretty close to done. So now test 1 is gone, and I got a message saying done test 1. So I want to use this to experiment with something. And what we're experimenting with is a callable function called fork. And fork is really the way that processes are created in Unix. And so we call fork, it doesn't take any arguments, it returns basically an integer. It's a process ID, but it's basically an int. And it says fork creates a new process by duplicating the calling process. The new process is referred to as the child process. The calling process is referred to as the parent. So this is like a bit of like cloning, right? If we go ahead and we just make a call to fork inside here. When this call is executed, the system will create a new copy of whatever process is currently running. And just like that, we'll have two processes. So let me go ahead and compile this. And let me run this in the background and do a PS. And hey, sure enough, there's two processes named test1. So if I do a PS-L, this first process, test1, its parent's ID is 67897. That's our bash shell. So this is the test1 that was created when I said, hey, run test1. This second process, test1, its parent's process ID is 68377. What is 68377? That's test1. So this second test1, that's a child of this first test1, which is a child of bash. So we've got new process creation going on here. The bash command was running. I said test1, which created this process, and that process called fork, which created a clone of itself, which was this process. 20 seconds have passed, so our original process has terminated, and that second process terminated. It would have told its parent that it was going away, but it doesn't tell the original bash process because, you know, bash was not this process's parent. So we've got to be a little careful with forks. If you do this on the Linux server, be really careful. Don't ever call fork inside a loop, for example, because it will do things different from what you might expect. So let's call fork 4 times. And at first glance, this might look like it's going to make, you know, 4 copies of our process. But in fact, it creates a lot of copies of our process. Right? And the reason is, you know, this first call to fork results in 2 copies of our process running. Each of those 2 processes now execute this call to fork. So now we have 4 processes. Each of those 4 processes executes this command, so we have 8, and each of those 8 processes executes this call, so now we have 16 processes all executing this sleep command, and that's what we have here. So as you can imagine, this can quickly overwhelm your system. If you do this in a loop, your system will crash. If you do it on the server, it should stop you from creating too many processes, but it can still make a bit of a mess. And if a lot of people do this, it can start to load down the system and potentially crash it. So, you know, Unix is not really made to be, you know, super secure, impenetrable, very stealthy, right? It's a very open system. You can look at all the processes that are running. You can, you know, see what processes particular people are executing, and you can consume resources recklessly if you were to choose to. And so be careful with forks. If you got your own system, especially a virtual box, you're welcome to play with this and make fork bombs and things like that. But don't do it on somebody else's system. Don't do it on the shared server. Don't do it on your main system if you're not ready for that system to crash. All right, so let's just go back to a single call to fork. And looking at the manual page, let's go down and look at what this return value is. And when on success, the process ID of the child process is returned to the parent. 0 is returned to the child. So if we were to say something like integer PID equals, PID will be different depending on which process is running. So let's print out the return value from fork is, and just print out the value of PID. Now remember, after fork executes, there are 2 copies of this process running. There's the original process, and there's the newly created child process. And so we should get 2 print messages saying return value from fork is, and the only difference between those 2 processes is going to be the value of this variable. If this was the parent process, PID will be whatever the PID of the child is. If this is the child process, then PID will be a 0. So let's compile this, and I can get rid of this sleep now. We don't need that. And so we run test 1, and we get 2 messages. Return value from fork is this, that was the process ID of the child, or it's 0, that means the child was printing this message. And each time we do this, we'll get a different process ID for the child. But other variables, let's enter an integer. Let's make a input array. Let's read from the user. And let's scan their input and save it in an integer called myVariable. All right, so what's going to happen here? We're going to prompt the user to enter an integer. We're going to let them type something in. We're going to scan what they type in. We're not going to bother checking for errors. We're going to save the integer they typed in this variable myvar. And then we're going to go ahead and we're going to say fork, which will create a second process. And then we'll print out the return value from fork, and we'll also print out the value of myvar. So test 1, enter an integer, I don't know, 1357. And the parent process said return value is 69951. That's the ID of the child. myvar is 1357. And then the child process kicked in and said the return value from fork is 0. Value of myvar is 1357. They both have the same value of this variable myvar, right? And they must have the same value because when you say fork, you clone the current process. Since myvar already had a given value, the newly created process has a variable myvar with the same value. Now it points to a different location in memory because it's a different process, but it's got the same value. The only difference between the two processes is this return value from fork. So we can pick up that process ID and use that to figure out who we are. So we can say something like, if PID equals 0, if the process ID is 0, print out I'm the child, otherwise print out I'm the parent. All right, so the parent knows that it's the parent and the child knows that it's the child. So so that's a way to create new copies of a process. And, sometimes we might just want 2 copies of a process running, but usually we're going to want one of the processes to do something different. And so they could, you call fork and both processes check the return value, and maybe if the return value from fork was 0, you're the child, you do something different from what the parent would do. So an example of this might be, you've got a video game you've written, and you want to save the state of the game periodically so that if it crashes, you can restore the game to close to where it was. And maybe, saving the game state takes a long time. Maybe you take a snapshot of memory and then you have to write that out to disk, and maybe that takes a few seconds. Well, you don't want to pause the game every 10 seconds while this writes out to disk, because that would be annoying. So every 10 seconds, you would go ahead and create a new process, and the parent process would simply continue playing the game, but the child process, which knows it's the child because fork returned to 0, would go ahead and open a backup file and write the contents of memory out to it. And it's a separate process, right? It's a process that's running at the same time as the original process that's playing the game. And, it's being time shared by the operating system, or it's running on a different core if you have multi-cores, and so on. So this is something that we'll do sometimes when we want to run some other set of code, but we don't want to pause a first set of code. We want both of these things to be happening simultaneously. And again, in Spring Quarter 223, we'll talk a lot about threading. We'll see some examples of this. We'll write some code where we have multiple threads, and we'll also look at some of the pitfalls and challenges of dealing with threads. All right. So the one other thing that we might want to do sometimes is create an entirely new process that's doing something totally different from the current process. And this happens, for example, when you're sitting at a prompt in Bash and you say date, right? Well, right now my program my process is Bash, right? Bash printed out this little prompt over here, and it's listening to me type, and when I hit enter, Bash is going to look at that and interpret it and say, oh, this person wants to run a command. But at some point we need to start running a different program. We need to run this program date, send its output to the screen, and then go back to where Bash was so that Bash can print out a new prompt and wait for a new command. So there's a mechanism for doing this, and the general mechanism is called exec, and there's a number of different versions of this. All right, so we're going to work with a version of the command called execl. There's all these different versions of it: execl, execp, execl e, v, vp, vpe. This has to do with how we want to pass information to a command. But execl, execl, is probably the simplest. And we can use this with basically two arguments: a path name and then the name of the command we're executing. So here's what we're going to do. We're going to modify our test function, and we're going to use it to execute a totally different command. All right, so I want to run the date command from inside my program. So if I look at, let me just do which date. If I say which date, date is sitting under /bin/date. All right, well, there's a really easy way to do this. I can say system bin/date, and let me put some print messages in here. So I'll say ready to run date, and then I'll say finished running date. All right, so system is a command that's going to take a Unix path and basically execute whatever is in that path. And it's going to come from standardlib.h. So let me go ahead and put standardlib in here. And let's compile this. I was in a different directory. So let's compile that and let's run test1. And it says ready to run date, and then it executed the date command, and then it said finished running date. So that's a really easy way to execute a command from inside a C program. But that's a very high-level function. If we look at the manual page for that, it's in Chapter 3. It means it's a high-level function, whereas these execs are sitting in, well, they're also in Manual Section 3, but they're lower-level functions. So here's what exec would do. So let's say execl. I'm going to say /bin/date, and I'm going to put in the name of the command as a second argument, and then I'm going to say null as the third argument. And yeah, null has to be uppercase. So I'm going to go ahead and compile this, and then I'm going to run it. Now, what's going to happen when it gets to execl is it's going to say, hey, let's find the binary contents in this file that represents, what needs to be loaded in memory to run the date command. Let's load that into memory and start executing. And so this is going to do something slightly different from the previous case. We're going to say ready to run date, and then we get this message, and then our program exits. And you notice it never said finished running date. The reason it didn't print finished running date is because once this call executed, this whole program disappeared. And now the process, instead of running this program, test1, was running date. And when date finished, it exited. And all of this is completely lost. So execl is the very low-level way that we go ahead and we create processes. And typically we combine that with fork. So we might say something like this. If fork equals 0, then let's go ahead and run date. Otherwise, I'll say I'm the parent. So I could have, other code after here that's doing something that I want my main program to do. But this section of code right here will create a new process. And if the new process is the thing executing this if statement, it will be true and it will go ahead and run date. So we'll get a ready to run date, the date will appear, and then this message will appear. But this message will actually appear from a different process from that one. So the behavior is pretty close to what we originally had with system, but you notice that I'm the parent printed out, and then our program exited, and we got our prompt back from bash. And then a little while after that, the child process turned into the date command and executed date. And so we'll leave it at this, but this is the first hint that there can be unexpected behaviors in how processes interact, unexpected ways that things time out. Things aren't always going to be sequential just because they look sequential in our code, right? This looks like we're going to print this, and then we're going to run date, and then we're going to say I'm the parent. But as soon as this fork is called, there's a separate process doing this. And in this particular case, the main process did both of its prints and exited, and bash came back to a prompt before that new process was able to complete the date command. So that's a little bit about working with processes, identifying processes on Linux. Like I say, there's a lot more you can do with this. This is really just kind of the tip of the iceberg, and we'll do a lot with processes in Java in CSE 223 in spring. But there's a bit of a teaser on how some of this stuff works. All right, thanks.